Hello, my name is Sebastian Bickel. I'm a research assistant from the FAU Erlangen-Nuremberg, working at the Institute of Engineering Design. Today I would like to present my paper entitled Comparing CAD part models for Geometrical Similarity, a concept using machine learning algorithms. To begin, I would like to give a short outline of my presentation. I start with a small introduction to the topic, followed by the general presentation of the concept. The concept is divided into the overview, a more detailed explanation of the similarity comparison with the projection method, and a description of the shape segmentation. Subsequently, I will present a case study of the concept and end the presentation with a conclusion and outlook. The whole concept is located in the field of smart manufacturing, which is defined by the National Institute of Standardization and Technology as a system which is fully integrated and collaborative and can react in real time to changing demands and conditions in a factory, supply network, or customer needs. This definition has been expanded to data-driven smart manufacturing with the idea of using data-driven methods and algorithms in the field of smart manufacturing. And now the application of these new data-driven tools is the motivation for this concept. Through using the geometries from smart design, a similarity search can be conducted to find similar, already manufactured parts. These similar parts have attached information like data for prototype production or evaluation metrics for the process simulation, which could be contact ratios or total equivalent plastic strain values. Therefore, the following steps are supported with the information and data from the previous parts. And the objective is to use the available data better through an automated search for similar parts, which should result then in a better usage of the already available data and a higher production quality within a shorter production time. Now I would like to give an overview of the whole concept in general. The idea is to differ between local and global similarity. So to start the process, a newly designed part and a part database is always necessary. For the similarity comparison, the part must be transformed into a shape descriptor. This descriptor is a matrix that is generated from the 3D geometry with the projection method. In the first comparison, for the global similarity, the whole part is transformed to a matrix and then compared among each other via the correlation coefficient. In this case, the projection method is used from the center of the part in contrast to the local similarity comparison. In the next step, the calculated scalar value can then be used for clustering the different results. This leads to parts being sorted in various clusters respective to their correlation coefficient. Subsequently, these clusters are examined individually and ranked internally based on the local geometric similarity value. This similarity value is now calculated with a special geometric feature of the searched part, which has to be defined by the user beforehand. The component is automatically separated by the system into different segments, and the relevant geometry parts are again compared for similarity. The two types of projection are presented in more depth in the following section because for the local similarity, the normal directions of the part or of the points in the point cloud is used for the projection. At the end of the process, each local cluster is ranked and finally linked to the clusters of global similarity. In the last step, an overall ranking is determined and the corresponding components can be displayed to the user. And now on the next slide, I would like to show you how this projection method works in more detail. As mentioned earlier, the similarity comparison has two different methods of projecting the 3D point cloud to a matrix. Therefore, in general, the objective of this comparison is to find similar components and to transform geometry to a shape descriptor, which in this case is the matrix. The whole process is shown here in more detail, and as always, it starts with the same geometry for both objects. So that's the initial part. which is then set up with the detector sphere around the part. For the both methods, it's again the same process, but now in the next step, that's where the whole method differs between each other. For the normal direction, the points are projected from the directional value calculated by the neighbors onto the detector sphere. For the center projection, as the name says, the first point is the center of the detector sphere. The second point is the point of the point cloud from the geometry. And then there's the intersection with the detector sphere. And now, for every pixel of the detector sphere, a pixel in the detector sphere is the segmented part. This counts the intersections from the projected lines, and this is now shown on the next pictures. So here the difference can be seen very clearly for the normal direction and for the center projection. The general detector sphere looks very different. And now the next step is the transformation into a matrix. This is similar to transforming a globe to a map. And these matrices are then the basis for the next step, the comparison with the correlation coefficient. Another very important aspect of the concept is the shape segmentation of the part. In this step, the mesh of the search part is segmented with machine learning algorithms into different areas. This geometric feature must be defined beforehand by the user, and therefore the whole process is supervised learning. The procedure in general is based on the paper Learning 3D Mesh Segmentation and Labeling by Kalogerakis et al. From 2010. But for the feature extraction and the classification, the algorithm has been changed and adapted. For the classification, a neural network was used with an own layout, which the results of this classification I would like to show next. The gray edges shows the result for the training data set and the blue edge for the test data set. In this case, all parts are from the case study and are therefore all sheet bulk metal form parts with the difference in the tooth geometry. And now for the input geometry, two example geometries can be seen. In the next step, the first classification of the part, the results are shown in red. So the mesh is colored red for the label tooth and gray for the label main body. The dataset was for the training dataset 150,000 times 550 for the training, and for the test dataset it was 50,000 times 550 features. This is the result of the classification with the own neural network, and now in the next step the clustering has been conducted to get a single tooth geometry. So only the areas of the part with the label tooth are clustered to get this single tooth geometry. And for the clustering, a DD-scan algorithm was used because it's capable of defining the number of clusters by itself. So you don't have to give him the numbers of clusters in which it classifies the geometry. So now, if you just look at one class, you can see that the tooth is now separated, and this is the necessary step for the local similarity comparison, where again, like mentioned earlier, the part is projected now via the normal direction, and so the correlation coefficient can be calculated and the two geometrical features of the part can be compared among each other. Now I would like to show a small case study of the whole concept to explain in more detail how it works for an actual case. Like mentioned earlier, the starting point of this whole process is the new part, which is designed here, which is the geometry with the number B, and you need a part database with the other 5 geometries. At first, a global similarity comparison has been conducted, and therefore the results can be seen here on the right side of the slide. So the first cluster, which is the cluster with the most similar parts, is geometry A and D, followed by a second cluster with geometry E and F, and a third cluster where only geometry D is classified in. So now in the next step, the first and the second cluster are examined on their own to get an internal ranking for the cluster. So now can be seen the segmented tooth geometry for the different parts. So here for part B, that's the tooth geometry that has been extracted automatically. And for geometry A, that's the tooth here. And for geometry D, that's the tooth geometry over there. Now again, a similarity comparison is conducted for the local similarity. Therefore, the normal direction for the projection method is used. And now an internal ranking for this specific cluster can be calculated as shown here. The first or more similar just on this local level is the first tooth geometry, and then the second is the second. The same can be done for the second cluster. Again, all the shape segmentation has been conducted, and therefore the different tooth geometries have been generated and the internal ranking is calculated. For the third cluster, obviously this is not necessary, because if there's only one geometry in the cluster, it's not necessary to segment the geometry even further. Now the internal ranking according to the local similarity value for all the clusters is calculated, which leads to the total result. Here it can be seen that the most similar part is geometry A, followed by the second, geometry D, the third is geometry F, the fourth is geometry E, and the last or most unsimilar geometry in this database is geometry C. This leads me to the conclusion and outlook of my presentation. What I've shown today is the concept for CAD part similarity search. The system is divided into the global and local similarity for a specific part. The separation for the local similarity is done with shape segmentation, which is based on supervised machine learning. The whole concept is supported with a case study using sheet belt metal formed parts. For the future, I would like to apply the concept on a larger dataset, for example, the engineering shape benchmark dataset. Furthermore, other similarity comparison algorithms should be used to improve the search. Thank you for your attention.